So welcome to the lecture today. We have to finish something from last week because last week we're not fully on time with the lecture. So we have to finish the lecture from last week. What did we do last week? Or what did you learn last week? Yeah?
About the
Mm-hmm.
reactive forces and their interactions.
Yeah. Okay, so we talked about adhesion. Do you remember what I told you about adhesion? What was very important for me when we introduced adhesion? There was something I said about this term here. Something we started, but we didn't finish last time. What is the force of adhesion? Yeah? We finished with van der Waals forces, but I highlighted very, very strong that adhesion is not van der Waals forces. What is adhesion? It's correct. We talked about van der Waals forces, completely correct. But what is the relation of adhesion and van der Waals forces? Yeah?
Adhesion is a relation of different chemical and physical forces.
Yeah.
And one of them is van der Waals.
Exactly.
The whole point of it.
Yeah. So adhesion is an umbrella term, and it's a force that particles stick together. And as you said correctly, van der Waals force is one part of adhesion. So we had here our van der Waals. And this is not the same. Adhesion describes how particles stick together. And van der Waals force, what is van der Waals force? Yeah? Yeah, very good. It's electrostatic interaction based on the molecules, and we can sum it up for particles. And basically it has to do with, we had a very important term related to it. What are the molecules? They are polar. Yeah, not all of them are polar. They are another term. Yeah? Yeah, the electronic negativity is a property of them, leading that they are a... What kind of moment? Not polar moment. Dipole, exactly. How many dipoles did we have? 3. Do you know the names? Kizom, Dubai, and London, right? Named after the scientists publishing the paper. And we took a full lecture to describe this. And in the exam, when I ask you the question, I want to see this. And I want to hear the explanation of it. I don't want to hear that adhesion is van der Waals force. I want to see that you understand these differences. We made an assumption. I said the model I will show you is for a quite special case. What is the special case? We said in air, right? So this model I show you is limited to adhesion in air. So means adhesion in liquid would give a different model, different forces. Some of them will not be there, some of them will come to it. What do you think is van der Waals force? Would it be in a liquid active or not? Do we have van der Waals forces only in air or also in liquids? Yeah? Exactly, also in liquids. Van der Waals forces are always there. Sometimes they are strong, sometimes they are not so strong, but they are always there. So now I would like to go to the second force. And the second force has to do with a question which we stopped last time, and this was, does the gecko stick to the Teflon pan? Yes or no? Sticks the gecko to the Teflon pan? No? Why not? How can we explain it here? Why does the gecko not stick to the Teflon pan? Yeah? Yeah? We discussed it, it's a good point, but this was not the explanation. Yeah. Why electronegativity? Yeah, and why? It's correct, it's less. Why? What was the important ingredient in the Teflon? Fluoride, right? Has an extreme high electronegativity, and the gecko could not activate this one. So there is no chance for him. Okay, then we also made a small explanation. A small calculation. So we took a very simple model, and the model was a sphere and a plane, and the sphere was mimicking a gecko hair, and the plane was the surface, the Teflon pan. And then we compared our calculation to these measurement results. Did you remember the result we calculated? Was it fitting the measurement results or not? Yes? Very well, right? And now the complex part comes. So far, I give you a very simple model, a Van der Waals force model, to perfectly describe what we measure here. But if you look a little bit closer into this diagram, you would see at ambient humidity or submerged in water. And the 12 nanonewton I showed you, we also calculated them, were at ambient humidity. And it seems that if we put the things in water, the force is less, right? So if you look, glass, glass, and then it's less. So you can take a look at the citation. What is the name of the paper from which I took this diagram? Yeah? So what could we take from here? Which information? Which information can we take from this title regarding our, yeah? It's a single measurement, that's correct, and we also calculated for one single, right? The sphere I showed you was one single hair, and they measured for one hair, but what did they want to prove with their measurement? Yeah?
Capillary forces are existing.
Yeah. So what is capillary force? Is it Van der Waals force? Is it an adhesion force? What is capillary force? Yeah? Surface tension is part of the capillary force. We will talk about this in a minute, very good. But what is capillary force? Quite general. Yeah?
It's the movement of liquid with the direction of gravity because of the adhesive force.
Yes, this is when you have a capillary. And then water is sucked through the capillary. But here we are talking about gecko and hairs and sticking. So what is evidence for capillary contribution? What could it mean? How could the capillary force be related to this one? Yeah? Yeah, but how? So this is two particles, or a gecko hair, and that's not a nice surface. And so far we said, okay, adhesion has a capillary, a van der Waals contribution, and this means we have dipoles here, right? And these dipoles interact electrostatically. This is how they stick together based on van der Waals. But what is now the capillary contribution? At ambient humidity, yeah? Yeah, very good. But this is related to surface tension. And this is, again, an explanation of the adhesion force. But how would they add or contribute, or what changed in this model? Yeah? Yeah. So what happens at ambient conditions? At ambient conditions, we have water molecules in the air. 50% humidity, 40% humidity. And if you have this small gap here, the water molecules will go in here. And more will go in here, and then something will happen. And this is the formation of a liquid bridge. And this liquid bridge leads to a capillary force. And the capillary force is another force which leads to adhesion. And what happens if I put this system in water, completely in water? What happens with my capillary bridge? So we're here at ambient condition, and now I take it and put it completely in water. What happens to this picture? Yeah? Yeah, it will be surrounded, and what will happen with this phase line here, or phase? Yeah? Yeah, there is no phase difference here anymore. So we don't have a three-phase system, and this means in liquid, completely in liquid, this capillary will go away. So there is no capillary force in liquid. And this is what you see here also in the measurements. So the capillary force adds in substantial amount to the adhesion force. While if we are in liquid, this would be away. Something else would pop up, but we will discuss about it. The dipoles would be there anyway. What happens if I'm at 0% humidity? What would happen with this picture? Because I said at ambient humidity, what would happen at 0% humidity? Yeah? Yeah. Exactly, so the water bridge could not arise. So now the question is, so we have these capillary forces and somehow they seem to have an influence, but why we get such a nice result in our van der Waals calculation? Because based on the calculation we did, we don't need this. And this is the trick with the Hamaker constant. The Hamaker constant is just a number. And if you have a very good value of your Hamaker constant, then the value should be lower, because the Hamaker constant does not consider capillary effects. However, you can measure the adhesion force of this system, as they did here. You can measure this force, and then you can say, oh, it's just van der Waals, and you can calculate a Hamaker constant. And the Hamaker constant is a black box around what happens here. So you have to be very, very careful. So basically, the Hamaker constant I gave you last time was not completely correct. The Hamaker constant was a strongly simplification that this is the same. And in the paper, and this is basically the assumption they made, and in the paper they tried to prove that adhesion for geckos don't work like this, but there is a capillary effect. And it is. So Now I would like to look a little bit more into capillary force. And the capillary force is quite simple. So we have two particles. We have a water meniscus in between. The calculations, the equations are always quite large, but this is the geometry because you have to describe the meniscus. And therefore you at least need two radii. Then you have the called circular assumption. So it means that the shape of the meniscus can be described by circles. It's a strong assumption, but it makes the calculation much easier. And there are a lot of angles. One angle is extremely important for capillary force. Do you know which one? Yeah? Contact angle. What describes the contact angle?
It's the angle where surfaces are
Yeah. But could you describe it a little bit? What is the meaning of the contact angle? Yeah?
I think it's the angle made by the surface of liquid with the surface, and it describes the mostly how large it is and the weightibility.
Yeah, here, this one, right? So this is the contact angle, and the contact angle describes the wetting of a liquid on a surface. And this gives you if a material is hydrophilic or hydrophobic. Depends on the contact angle. And contact angles for particles are very hard to get because a contact angle is normally measured on a flat surface. That's extremely simple. You take a droplet, put it on a surface, and then you make a picture, and you do it with different, no, for the contact angle you just do it, then you can do it with different liquids and you can calculate surface energies. But for particles, it's not the same as for the material because the geometry has an influence, but we don't know what is really the influence and we don't have good measurement devices. I would love to have one, as you know from your project work, but it's really not so simple. So we do a lot of assumptions here. Okay, but at the end, what do you think? Capillary force, contact angle is important, so is capillary force in here the same if I have a hydrophilic or a hydrophobic system? Yeah? No, why not? It's completely, so when is the capillary force stronger, in a hydrophilic or in a hydrophobic? Hydrophilic, right? Because hydrophilic means it sticks perfectly. Hydrophobic means not so much, and this is also a quite good question because is Teflon hydrophilic or hydrophobic? Hydrophobic. So, and then it's a little bit questionable what is really the capillary effect and how the capillary forms between the gecko hair. And so you see, it's not such a simple question. Actually, we do research till today on it. Okay, so the capillary force, similar as the van der Waals force, depends on two kinds of forces. And you named them already. And these are two effects which are not described in the van der Waals model. So capillary force is again an umbrella term for two effects. What are the two effects? It's Fp and Fs, yeah?
surface tension.
Yeah, very good. So we have surface tension. So depending on the liquid, the surface tension here will increase or decrease the sticking, right? If I have honey, that sticks a lot. If I have water, it's okay, but not as strong. Yeah, the second one? Exactly, the pressure difference. Why the pressure difference is important here? Why the pressure difference? Or where is a pressure difference?
Inside and outside.
Yeah. So where is the pressure higher? Here or here?
Outside.
Outside is higher and inside is lower. So what happens if the inside has a lower pressure. Yeah? In which direction? Yeah. Yeah. So it's like suction, right? It sticks together. So, and how do you know where the pressure is higher or lower? How can you see it even from the image? Yeah? Exactly, the shape of the meniscus. So if the meniscus has a straight line, the pressure is the same. There is no pressure difference. But Young-laplace equation tells us that a curved meniscus leads to a pressure difference. So here is the force based on the surface tension. This is what you see here. And as I said, the equations are a little bit longer than for the Hammaker approach, but this is due to the geometry of the meniscus. And here is the force based on the pressure difference, and these two things add up to the capillary force. So we have another one here, and this is F capillary, and this is in air. Yeah? Yeah, that's a very good question. Are van der Waals and capillary forces related to each other? What do you think? Yes or no? Just look at, is this one related to this one? Yeah?
I think van der Waals is because of capillary force, but what we calculate here is the van der Waals force between two grains, and with capillary force we calculate the effect of humidity.
Yeah.
And the direction of the particle.
Yeah, that's a very, very good point. So as you said, the van der Waals force is the reason for capillary forces. So basically, the interaction of the molecules, this kind, happens in the meniscus between the water molecules, right? And this leads to the formation of the meniscus. And the meniscus gives a pressure difference. And the van der Waals model don't has a pressure difference. So if we don't have a model giving this effect of pressure difference, our model would not describe correctly what happens here. Also, the van der Waals model don't describe the effect of surface tension. But van der Waals forces between the molecules are the reason of surface tension. But this is not what I calculate here in the model. Here I calculate the van der Waals interaction between the particles and, depending on the model, between particle and liquid. But these two things are there because of the molecular interaction, because of van der Waals interaction, but they are not in our adhesion force model, okay? But you see, it's not so easy to set the correct boundaries of the model. It's really not easy. If the number fits, you can say it fits, okay, good, but is the model correct? Or is it just luck that the numbers fit? And what is when you want to make predictions? Good. I just want to go with two slides through the two terms. So we have surface tension and pressure difference. I think you know these things. So surface tension is the work necessary to increase the surface area. And this means we have there a liquid. And if you go in the middle of the liquid, the molecule is surrounded by an equal amount of molecules, and there is no reason for the molecule to go to any direction, just due to thermal movement it moves, but there is no force from the liquid itself. But the closer the molecule goes to the surface, the less it's surrounded from the top, and the more it's surrounded from the bottom. So it means there is a force pulling it back or holding it back. And if I want to increase now the area of my liquid, I have to fight against this force, because the force holds them like they stick together, and I want to put them, I want to increase the area like this, but there is a sticking force, and this is adhesion force, or correctly termed for the same material, it's cohesion, and this leads to surface tension, and surface tension has a really weird unit. What is the unit of surface tension? Unit per, yeah? Newton per meter, and why it's weird, or is okay? What is the unit of tension? Newton per square meter, exactly. So did I make an error here? No, I didn't make an error, and this is what you see in the definition. In the definition, you see that the surface tension is the work you need to increase an area, right? So the work I have to put in to increase the area. And if you put in the numbers, so work is force times distance, right? So if I have my liquid and I would like to stretch it over a certain distance, this is the x, right? I need a force to stretch it over a distance. And the area, and this is basically for I don't have so much space, for an idea that I have a liquid here, and I want to pull it in this direction. And the counter force here, this is surface tension. And the delta x is the stretching, and L is the height. So you can think about a frame, and we have soap or something in between, like these bubble, how it's called, these, wie heißen die denn? Seifenblasen. How it's in English? Bubbles. Bubbles? Maybe next time I will bring, I have some in my office. So a frame like this, right? And I want to put a little bit air in this. And therefore I have to overcome the surface tension. So if you put in the numbers, so you have x, F times delta x divided by 2L delta x. So this is the new area arising here. The x cancels out, and then we have force over meter. So unit fits, okay? Good. And this is why this tension is different. So the same, or not the same, this is for pressure difference. And for pressure difference, as I mentioned, we have Young-laplace equation, and this says that we have a curved interface, and at the curved interface, there is a pressure a pressure difference, and the pressure difference goes from liquid to gas. If you don't do it in this way, you get problems with your plus and minus and with your numbers. And in this case, you can calculate if the pressure in a droplet is larger than in air, or in a bubble is larger than in water. And this also is one part of the capillary force. Good. So far, van der Waals force, capillary force. Both of them, are we finished now? That's the question. What do you think? Are we finished or are we not finished with our adhesion model? Yeah? No. If I wouldn't ask the question, right? So what could, again, play a role here? What do these two have in common? If you think about aerosol technology. And I told you the size is very, very important. And we had Knudsen numbers. What was important in this case? Or what was the meaning of Knudsen number? Yeah? No, it's not about convection. No. What is in the Knudsen number? We used it to figure something out, right? What do we want to figure out? Or why we use the Knudsen number? Yeah? No. Not velocity. The regime, what kind of regimes? Yeah? What kind of regimes? Free molecular or continuum, right? So we had two regimes, free molecular and continuum. Continuum for large or small? Continuum small, large, small, okay. No, for large. Continuum is large. Everything is the same. So what kind of equations are these equations? Which regime? What is this for an assumption? What is this kind of a regime here, or this here? Yeah?
Because these forces are effective just for small particles.
Yeah, but is this a free molecular depiction of water? Yeah?
It's continuum because we don't care about the molecular interaction. We
Yeah.
consider them as a whole.
Yeah. So it's continuum because water is water. It has a density, it has a temperature, whatever, but we don't consider single individual molecules here. We consider the effect of the molecules, but we look at a black box, it's water. We don't count individual molecules here. Also in the Hammaker approach, the Hammaker model is a continuum model. By integrating, he just makes a black box out of it and says it's one area, right? He don't kind of considers each individual molecule. But there is a question, and you said the particles are very small we are talking about. So they are more or less in the same size as molecules. So we enter for nanoparticles. If we have 10 nanometer, we enter a regime, the same we had in diffusion, right? We enter a regime where the nanoparticles or aerosol particles can feel or see the molecules. And this is not considered in these two models because these two are continuum. And there is a third model, and this is what you see here. And it describes pressure, no, not pressure differences at surfaces. It basically describes also pressure differences, but the headline is wrong. So what it describes is you have two surfaces, could be anything, and in between these surfaces you have molecules. And now you can imagine that depending on the distance of the two molecules, there are distances which the molecules really like, and there are distances which the molecules don't like. Because if you make the distance too close, the molecules will work against this, right? They will repel each other, and you have to apply a force to press them together. It depends, of course, on the amount of molecules you have in your gap. And the same is that if you reach the perfect distance, each molecule is where it likes to be. It has the perfect distance to its neighbor. And then you want to go out again. The molecules will not like it. So you again have to apply a force. And what could happen is that with increasing distance, more and more molecules, like water molecules going into the meniscus, right, from the ambient humidity, more and more molecules come in. So you not only have one layer, you have multiple layers of molecules. And for each layer, there is a distance the molecules really, really like, and the system will automatically go to this distance. And you have to apply a force to bring them closer together or to pull them out. And this force is called solvation force. And here is one of the first measurements from Israel Yachvili in the 80s. And there he clearly shows that this is between two mica sheets, so very thin planar sheets. And he used quite large molecules because then he can detect these effects. And you see these waving behavior. And these waving behavior so here is the force and here's the distance. And you see that the force goes from repulsive to attractive, from repulsive to attractive. Minus is attractive, plus is repulsive. And this always has to do with the structuring of the molecules in the gap. If the gap is perfectly, you have attractive force, and this will not go away. And on the right-hand side, you see the van der Waals force here. And this is based on the Hamaker model. So he calculated for the Hamaker model the system, and then he made his measurements. And you see that they don't match very well. Because the van der Waals model is just, or the Hamaker model, sorry, is just a straight line because it's continuum. It does not consider these structural effects. And this means we have a force which is non-continuum, and this force is part of the adhesion model, Solvation. And this is a molecular model. And now we have to consider all three things. We have to consider that we have van der Waals forces, we have capillary forces, and we have solvation forces. However, it's important, the solvation force is the force which comes from the fact that the molecules don't like the distance, or they like the distance. It's not the pure interaction. The pure interaction, again, leads to the fact that they like or not like. But it's like the pressure difference, an additional effect. And basically, this is what I try to do in my research, is to bring these things together. So here you see that we made some measurements, so we developed a method, then we can measure the force between single nanoparticles. So what I can do is exactly for this picture measure the force. And this was before not possible because you could measure forces between thousands of particles, but then the model doesn't work. How do you calculate with this model for thousands of particles? So you need a method to measure between only two particles. Then you can do these kind of calculations. And this is what I developed. And then we made some molecular dynamics simulation because you have the experiment and then you look into the computer. And this is what you see here. This is the molecular dynamics simulation. These are titania nanoparticles surrounded by water, 50% humidity. And you see there is a capillary here, right? But you see the capillary looks different. It doesn't look like this because you can count the molecules. On this size scale, the molecule, it's not continuum. So, and at the end, the model I suggested was basically only these two. Why these two? Because in the correct model of the solvation force, this one is already incorporated. Because the van der Waals force leads to the solvation force, and they leads to how the molecules kind of arrange. This is based on van der Waals force. The van der Waals force governs how they arrange. So in the solvation force, you can have already the van der Waals force, but you have to also be sure that you have the structural effect, which is the key of the solvation. But surface tension and pressure difference, you don't have here, you don't have here, and this is what you have to consider. And if you ask me, this, what you see here and here, is what happens between a gecko hair and a surface. But proof has to be done till today. It's not proven. That's just my hypothesis. This is what happened. This is basically the reason for gecko adhesion. here I really like the poster because it was made by a student. Basically, it's all together. So here we measure, then we have the simulation, we have a mathematical model, and here you see basically the same depiction. Where it is? Here. Here you see the same depiction as here. Okay. And you see also that it's a little bit small, but you see that at the capillary, it's also a little bit more complicated, because the capillary can arise due to two things. And this is basically the pure meniscus. But what also can happen, and this happens at the nanoscale, is that each surface, if it has a certain hydrophilicity, has water on. Right here's water on the surface, a few molecules, a few layers of molecules. And if the nanoparticles are so small, and you see it in the simulation, basically the meniscus arises just from the overlapping of the water layers. So one particle carries 1 or 2 layers of water with him, and the other one or her carries 1 or 2 layers of water. And if they are close to each other, these water layers overlap, and this gives a meniscus. So it does not necessarily has to be this macroscopic humidity goes in. Good. Any questions? Yeah? Yeah, that's a really, really good question. In my opinion, hydrogen bond is van der Waals forces. It's a little bit stronger because of the molecule, and of course it's a little bit in between because it also has certain directions, right? But hydrogen bonds, and this is what you find very often in literature, but hydrogen bonds are already in here or in here. They're just stronger. But we have some papers, and I really don't like them. Actually, I was not in the papers, where the hydrogen bond was an additional part in the equation. But then you have to be really careful if you not count something double. So solvation force. Because the van der Waals and the solvation model explains the interaction of the molecules with each other. And hydrogen is just how the water molecules interact with each other. So it's nothing new, like the pressure difference, the surface tension, the structuring or something. So, but I never really made research how correct this is, or if hydrogen bond have to be considered in the case of water as an additional one. In my opinion, not, but I don't have proof for it. Any other questions? Good, then we are finished with this lecture. So I hope you know adhesion, and I hope you understand the model, see that it's quite simple and not so simple. It's very simple to write it down, but it's not so simple to make the correct boundaries. But I want you really to explain each part, and also to argue a little bit how to make boundaries and so on. We talked a little bit about application of adhesion. And with this, we can go to the next